Om Swastiastu. Assalamualaikum warahmatullahi wabarakatuh. Salam nama budaya. In this video, I will explain about chapter 12. Metallurgy for the non-metallurgist. But first, I want to introduce myself. My name is Dr. Putra Hutabarat with student ID number 2305531075. I am from Mechanical Engineering Study Program from Engineering Faculty and Udayana University. Next, this main referencing. Next, chapter 12, stainless steel. Stainless steel is a special class of steel alloys known primarily for their corrosion-resistant properties. The stainless characteristics associated with these alloys are achieved through the formation of an invisible and adherent chromium-rich oxide surface film that, when damaged, has the unusual ability to heal itself in the presence of oxygen. 12.1 The history of stainless steel. During a visit to the Royal Arms Munition Factory, Barely was asked for his assistance in developing an alloy for use in rifle barrels that was more resistant to the erosive action of the hard discharger gases that were produced during firing. Barely decided to experiment with chromium as an alloying agent because he knew that alloying with chromium raised the solidus temperature of plain carbon steels, and that chromium steel alloys were being used at the time in the manufacture of aircraft engine valves. He produced a number of different experimental heats of steel with chromium contents ranging from 6 to 15% and with varying levels of carbon content. When Barely attempted to patent his invention in 1915, he found that Heinz had already registered a patent for this type of alloy because the directions at his company envisioned little promise in the commercial development of stainless steel. Barely and Heinz subsequently put their sources and together with a group of investors formed the American Stainless Steel Corporation. Next, 12.2 Modern alloys. Many new stainless steel compositions have been invented and commercialized over the years since the initial discoveries of these alloys were made. One of the reasons for the popularity of stainless steels, in addition to their corrosion-resistant properties, is their versatility in processing and application. With some restriction, stainless steel can be saved and fabricated by conventional processes such as casting, rolling, and forging. They can also be fabricated using standard powder metallurgy or PM practice. Alloy designation system. There are several different designation systems that have been developed for stainless steel alloys, the most basic of which is the differences between the wool compositions, the casting compositions, and PM compositions. In the United States, raw grades of stainless steel are generally designated by the American Iron and Steel Institute or AESE numbering system and Unified Numbering System or UNS, or the proprietary name of the alloys. Next, other thermal treatment processes such as nitriding to enhance surface hardness, for example, may also be performed with certain grades. Table 12.2 lists the respective stainless steel families to which several of these practices are generally applicable. Next, 12.3 Austenitic stainless steel. Austenitic stainless alloys are among the most common grades of stainless steel. They are classified with AESE 200 or 300 series designations. The 300 series grades are chromium nickel alloys, and the 200 series represent a set of compositions in which manganese and or nitrogen replace some of the nickel. The properties of the 200 series grades may differ appreciably from those of the 300 series, with higher strength being the most significant difference. Their austenitic microstructure is very tall and ductile, which allows these grades to be used successfully in applications ranging from cryogenic temperatures up to the elevated and operating temperatures and collectorate in furnaces and jet engines. They are heat treated primarily for full annealing or for stress relieving, and in some highly specialized applications they can be treated to enhance surface hardness. Austenitic stainless steel are also generally the most grade resistant of the stainless steel alloy. This figure 12.4. Next, the austenitic stainless grades process chemical composition that fall within the austenitic region of the scapular along diagram shown in figure 12.5. This diagram was developed to illustrate the various types of paste that are present in stainless alloys in the solidified condition, such as found in wheels and castings. Other alloying elements are also used to impart or enhance certain properties. Silicon is used as an alloying element in austenitic stainless grades to promote oxidation resistance and the resistance to corrosion by oxidizing acid. Copper is added to promote resistance to sulfuric acid attack. The rare earths contribute to the formation of a more stable oxidation-resistant surface scale. Niobium in copper amounts generally extends elevate temperature grid resistance, and sulfur and selenium addition are used to enhance mechanability. Next, 12.4 Ferritic stainless steel. Ferritic stainless steel are relatively low carbon iron chromium alloys classified with AESE 400 series designations. They are generally grouped into around 10.5 to 12% medium, or around 16 to 19%, and high greater than 25% chromium contents. With some notable exceptions, they are generally not allowed with either nickel or nitrogen. The ferritic stainless steel have relatively poor high temperature strength and exhibit limited low temperature and large section thickness. In general, their corrosion resistance is substantially lower than the austenitic stainless steel but higher than most of the martensitic grades. Figure 12.6 lists the relationship between alloying and the resulting properties and processing characteristics of the standard ASE ferritic stainless steel. The ferritic stainless steel are ferromagnetic at room temperature and possess generally good ductility and formability. The mechanical properties of the ferritic alloys are similar to the austenitic alloys in terms of strength, but they generally lack the ductility of the austenitic grades. They are used mainly in the form of light gauge sheet because their toughness drops off rapidly in heavier sections. They do not have the high temperature strength of the austenitic steel, figure 12.7, and due to their body-centered cubic or BCC crystal structure, ferritics are generally unstable for use in cryogenic applications. Sigma phase. When ferritic stainless steel are held for extended periods of time within specific temperature range, they can be subject to embrittlement due to the precipitation of an intermetallic compound known as sigma phase. Sigma phase is an iron chromium compound with a tetragonal crystal structure and hardness equivalent to approximately 68 HLCC or 940 HV. Next, 12.5 duplex stainless steels. Duplex stainless alloys consists of two phases at room temperature, austenite and ferrite. Figure 12.8. The duplex stainless steels can generally be regarded as chromium molybdenum ferritic stainless steels with sufficient nickel, used as an austenite stabilizer to create a balance of ferrite and austenite at room temperature. The duplex stainless steels were originally developed in the 1920s but did not gain popularity until recently due to an increased need for stainless steel with improved strength and better resistance to chloride-induced SCC. Table 12.10 lists the duplex stainless steel currently covered by EU and its designation. They have low carbon content, lower 0.04%, with typical chromium content varying roughly between 18 and 30%. The content approximately 3 to 9% Ne. Other alloy additions, including molybdenum, nitrogen, tungsten, and copper, are used to impart specific properties. Some of the first generation duplex grades, such as ASE type 3 to 9, achieved the phase balance between ferrite and austenite primarily through nickel addition. These early duplex grades have superior properties in the annealed condition, but segregation of chromium and molybdenum after welding often significantly reduces their corrosion resistance. The addition of nitrogen to the second generation duplex grades helps to minimize the effect. Next, 12.6 martensitic stainless steel. The chemical compositions for a variety of martensitic stainless steel, their chromium content is generally in range of 10.5 to 18%, with carbon contents spanning a wide range from as low as 0.04% to as high as 1.2%. 12.6.1 Heat treatment of martensitic stainless steels. Preheating. Parts that should be preheated prior to annealing or hardening operations include parts with heavy or thick sections, parts containing several geometry changes, parts with both thick and thin sections, parts with sharp corners and retracted angles, heavily ground parts, Mesin parts with heavy deep cuts, cooled format of strikenet parts, previously hardened parts that are slated for reheat treatment. Next, annealing. Annealing temperatures used for subcritical, isothermal, and full annealing of martensitic stainless steels, along with the resulting values of hardness, except for each of these respective annealing practices, are shown in Table 12.13 for a selected number of grades. Hardening mechanisms. Martensitic stainless steel are hardened by austenitizing, quenching, and tempering. The metallurgical mechanisms responsible for the martensitic transformations that take place in the stainless alloys during austenizing and quenching are essentially the same as those that are used to harden lower alloy content carbon and alloy steels. Hydrogen embrittlement. In substance, hydrogen exposure occurs during melting, heat treating, or chemical processing, such as in breaking and electroplating operations. It may result in hydrogen embrittlement in martensitic stainless steel. This effect occurs much less frequently in ferritic grades and is essentially absent in austenitic grades. Next, precipitation hardening stainless steel. Rock precipitation hardening or PHH stainless alloys are designed by the HSE 600 series and also by non-standard proprietary compositions. However, the UNS designation and the proprietary names of these alloys are often used with greater frequency than the AESA designation. Table 12.15 lists the chemical composition of the more common PH stainless steel. Of all of the available stainless steel grades, they generally offer the greatest combination of high temperature coupled with excellent hardness or corrosion resistance. Semi-austenitic PH stainless steels are essentially austenitic in the solution anneal condition. After fabrications operations are completed, they can be transformed to be martensitic structure through cold and austenite conditioning. The treatment that converts to the austenite martensitic. Next, martensitic PH stainless steel are the more popular commercial grades because of their relatively high hardness in the solution anneal condition, and the martensitic grades are used principally in the form of bar, rod, wire, and heavy forgings. They can also be produced in cold rolled sheet and strip, but these forms typically represent much smaller production volumes. The semi-austenitic grades are used more frequently in sheet, strip, and wire forms, and are often selected for applications that require extensive forming prior to hardening. These alloys are used in applications such as injection molding, jigging, die casting, forgings, and fasteners in the aerospace industry, and a wide variety of other applications requiring significant strength coupled with excellent corrosion resistance. 12.8 Cast stainless steel. In general, the cast and work stainless steel possess equivalent resistance to corrosive media, and they are frequently used in conjunction with each other. Important difference to exist, however, between some cast stainless steel and their work counterparts. One significant difference is in the microstructure of cast austenitic stainless steel. There have been 4 SCC failures with cast stainless steel in comparison to the approximate metallic equivalent raw composition. The principal reason for this improvement resistance are apparently alloying with silicon to improve fluidic forecasting operation provides an added benefit from the standard point of CCC. Sand castings are usual tumbled or sandblasted to remove molding sand and scale, which may place the surface in a mild state of compression. Next, cast stainless steel designations are prefixed by 2 letters. The first letter of the designation indicates whether the alloy is intended primarily for liquid corrosion surface or C, or for high temperature surface H. The second letter denotes a nominal chromium nickel type of the alloy feature 12.10. As nickel content increases, the second letter of the designation is changed from A to Z. From A to Z. 12.9 Powder metallurgy stainless steel. 3 out of the 5 families of stainless steels, namely austenitic, ferritic, and martensitic, are immensely suitable for manufacture via conventional PM processes. Select alloys from all 5 families can be processed via metal injection molding or MEM. The martensitic grades are used for a wear resistance, while alloys from the ferritic and austenitic families represent the bulk of PM stainless steel grades. Next, standard PM stainless steel designations are listed in table 12.19. In addition to the standard PM stainless grades, a number of non-standard grades, custom and proprietary alloys are in widespread use throughout the PM industry. In contrast to their raw counterparts, such alloys represent a significant portion of the total number of available PM alloys. This is partly due to the fact that the PM process is highly flexible and amenable to the development of custom alloying via sintering of microscopic mixtures of metal powders. Also, compared to the world steel industry, the PM industry employs much smaller melting furnaces, which makes it more amenable to the production of custom designed alloys. Next. Okay, I think I can explain about chapter 12. If there are error in reading, please forgive me, and I want to say the last. Om Swastiastu, Assalamualaikum warahmatullahi wabarakatuh, Salam Nama Budaya, and thank you for watching my video, and goodbye.